So if you go under content, there will be two things that you'll be able to see. One of them I'll be able to see already, and one you'll be able to see at 11 o'clock. So if you have a QuickTime plugin, this will come up. If not, you can just press download, and this will be a video that I went over a lot of detail in how to prepare a resume. The resume and all that information is under professional development. I go in tremendous amount of detail in the video about where to find it, what you should be doing, things employers are looking for, things employers don't want you to see. One thing I do want to note here, as this opens, this sample resume for students, this format that I have here was provided to me by Intel's Veterans Group. Basically, what they're trying to do is they're trying to help military veterans convey their qualifications properly. So you have a resume sample from the top company in the world in electrical engineering, and you all are either computer engineers, electrical engineers, or computer scientists, right? So this is what they want to see in this kind of format. So do you think it's probably a good idea to switch up your format a little bit to make sure that the top company in your area? Probably a good idea, right? So, but I go into a lot more detail of what you should and shouldn't do there. I did want to have one little video here. This is another thing that Intel provided. It's about a minute long, and it's 9 phrases on your resume that are making hiring managers cringe. And this is the screen here. Yeah, don't need to put references available upon request anymore. If they like you, they'll ask for somebody. Okay, so what they mean by that. Other thing I have put in here in a professional development, it's this document that says Power Verbs for your resume. This also came from Intel, right? So if it ever decides to actually download, basically you want to speak in active voice, not passive voice. You want to say, directed this project, organize this. You want to basically, and I go into a lot of detail in the video I posted, but basically what you want to do is ensure that your qualifications meet the job description. So on your take-home exam, which will be at 11, all right, that's going to get annoying really fast. All right, so I found a job listing on AMD. You know, are familiar with AMD, the company? That you would actually, it's for a digital design engineer for students that are just graduating and either have a Bachelor of Science in Computer Engineering or Electrical Engineering. Sound familiar? Yeah, that's you guys. And so basically, I want you to tailor your resume to this specific job. And I found 3 jobs that as the semester progresses that you'll be qualified for, that you'll be able to tailor your resume more and more. So you get 3 cracks at improving your resume, 3 instances of feedback from me. And then the second part is being able to go through and actually prepare for the exam. So the 55 points there for those kind of questions are actually you getting credit for studying. So then the in-class portion is the actual combining concept, kind of the putting the problems together. Also, so it's simulating a job interview. So that means even though there's certain definitions that I'm asking on the take-home portion, if I sit from went over it in review, I would expect you to be able to produce it in class. Now, why do you think that is? So basically, the simulation process is go over this important concept. In fact, if you actually, I bring up the exam portion that I've posted. It's not available until 11 o'clock. That's to keep you guys so you pay attention to what I'm saying today. But it will be there at 11. And just so you know, I'm not crazy. On the actual, well, that doesn't necessarily mean I'm not crazy. But one thing that said, good understanding of computer organization and architecture, right there. So obtaining the job, update your resume, and to give you guys a little motivation, I went on Glassdoor and found what they're offering for this particular job. It's only $101,000 a year, and you'll be qualified for it at the end of this semester. So put up with me a little bit, and you'll get paid. Second part, even though number one, define and differentiate clearly between computer architecture and computer organization, give 4 examples of each. This is preparing for the interview. So if you prepare for something, you should be able to produce it on the day of the interview, right? So the same thing. You should be able to actually say it in class. Now, one question I'm commonly getting, and the answer is going to be no. Do I have to dress up as though this is an interview? No. I mean, a lot of people are asking about it. It's a fair question to ask. And some people were actually, other professors recommend, if you're going to do this, you should actually have them dress up. However, I can't guarantee, obviously, that you will have actual interview clothes here or that you have enough money to be able to afford them at this given moment, right? So make sure you wear the appropriate clothes that don't get you arrested by the university police. And that's my one requirement for this class. But other than that, I go in a lot of detail in the video that should be able to help you out. The thing about the resume, a lot of people are kind of concerned that I'm going to hammer them if you guys do it wrong. What I want this time is an obvious effort and attempt at doing it right. After that, I can fix grammar without taking points, right? I can say you should probably write it this way and probably write it that way. What I want to see is the effort. If you show me the effort, you'll do fine. I've looked at hundreds of resumes. If you put no effort into it, it's obvious, and I'll be able to tell, okay? And that's where you lose points. So just make a good faith attempt. You're going to get 2 more cracks at it. You go, oh, okay, he meant this. I should say this. Do the second time, you do a little better. The third time, then you get my feedback from the final, and then you suddenly have a really good resume, right? Cool. On that note, what we're going to do today is get started on MIPS to C coding. So up to this point, we've talked about this, we've kind of alluded to this computer architecture. And we talked about performance, we talked about computing arithmetic, we kind of made those allusions to memory hierarchy. We have average memory access time, and I've talked about base addressing, registers, instruction memory, pseudo-direct, and PC relative addressing, right? So everything that you've learned, plus for some of the things we're going to go over early in this section, you actually know enough to be able to take some C code and convert it to assembly language and then machine language. Now, a lot of you have not had C, so we're not going to go into too much detail. But where people always get tripped up when they're trying to learn C, and it's like a make or break concept, is pointers. And how many, suppose you have taken C++, was pointers fun? No, they were brutal, right? Now everybody's saying, look, oh God, no done again. And part of the reason why they're brutal is because it can be hard to visualize precisely what a pointer is. So in this section, what we're going to do is I'm going to tell you physically what's going on in a pointer. So well, I won't go into too much detail, but you'll have like a pointer to an integer and a pointer to an array, and it looks the same. So like it would be int star sum and int star var, where var is the integer and sum is an array of integers. And it looks the same, and that confuses the heck out of students. But if you understand what's physically going on, and you understand what base addressing is, and you understand PC relative addressing, it actually makes a lot more sense and helps you code so that when you take organization next semester, you'll crush it. When students take my class and then take organization next semester, they often say it's very easy. So So this semester hard, next semester not so hard. So there we go. So you're gonna have to answer my questions or I can get back at you, right? Do it. There we go. Error in answer or. All right. So we talked about addition and subtraction in the arithmetic logic unit, right? And let's see if I can move this. So there we go. I can see it. Also recall the MIPS green sheet that we have these values that talk about RS, RT, and RD. When you see this notation, R of RS right here, what this means is that's the value in register RS. So R of RS. So the addressing tells me to get this 5-bit value. Then we use a 5 to 32 decoder, right? Remember that? And then we go into the registers, and this pops out a 32-bit value. That is R of RS. Does that make sense? So register transfer instruction is the idea of RD. R of RD is equal to R of RS plus R of RT. Now, if you're looking at the job description that I post on the exam, you're going to see something called RTL, which is Register Transfer Language. What we're going to be going over in this section is taking C code, which is on your job description, and converting it to Register Transfer Language, and then turning it to the machine language, which means we're actually going to represent, when you see C, what does it actually mean in zeros and ones? And then we're going to be going over a little bit of C, but specifically why C is so commonly used, especially in electrical and computer engineering applications, like application-specific integrated circuits or embedded processors, because the whole point of C is to compile it down efficiently to the compiled code. And so I've alluded to this a little bit already. We have MIPS has two registers, two source registers, and a destination register, and an R-type instruction, right? We had RS, RT, and RD. So you have to add 2 and put it into a third register. So in this case, in example 4.1, we have an instance where we're adding up 4 variables here, B, C, and 3, B, C, and D, right? And then we have S1, S2, and S6. So if you recall from the top of the guide objective, what is S, any variable that's referred to as S? What does that mean? Save. Very good. It's a save register. And so does T, what does T stand for? Temporary. So the reason why I had you do that TGO is S starts at 16. So S0 is 16, which is binary value. I'm going to pick on this roll. What is 16 in binary? Very good. Exactly good. Office hours worked out really well, right? Yeah, exactly right. There we go. So if what's then 17? Just add 1. Right? So S6 is 16 plus 6, which is 1, 1, 1, 0. And that's your numeric value that indicates that that specific register, when we get our decoded value from our registers, we want that 32-bit value, right? So what we have to do is we have to then get these values, add them together, and then store them in the register A. Register A is then stored in S0. So the first thing we have to do is so this is one line of C code. Very basic line of C code. A equals B plus C plus D, right? You can do the same thing in Java. You can do the same thing in C++. You can do the same thing in C#. Very basic line of code. So now we're going to compile it down. First things first, we have to go in order. This is something that I'm going to say over and over and over and over again as we get into C code. You have to do what the coder tells you. You have to do high performance execution of compiled code. The compiler can only do what you tell it to do. So if you do P plus C plus D, but you do it in some sort of weird order, unless I explicitly state that there's a compiler optimization for that, and where the best case one is, if statements, because you can actually reduce the amount of code by switching them back and forth. If I equals J or I less than J, you can actually improve it that way. But otherwise, you kind of have to do it in this order. Now, you can't do A equals B plus C and A equals A plus D. And the reason why, and I think I've mentioned this before, is the coder never says that A is equal to B plus C in the code, right? So you can't do that. What you have to do is you have to use, as you all mentioned, a temporary register. So the first thing we do is the notation's a little different. So if you remember from R-type instruction, you have your opcode, you have RS, RT, RD, shift amount, and your function, right? In this one, they're backwards, because this is the register transfer language. This is RS, this is RT, and that's RD. I'm pointing this out only because this is something that typically confuses students, so I want to make sure it's absolutely clear. So what's happening here is we're actually going add. Now, does anybody remember the value for all R-type instructions for the opcode? I heard somebody say it a little louder so the whole class can hear it. No, not 6. 0. Very good, Alex. It's all 0, right? So if you look into the R-type, if you look at the MIP screen sheet in your text, on the very front page of your textbook, so you got your front page of your textbook there. If you look at any instruction that says R-type, it'll say 0/ and then some sort of function, right? That is because all R-type instructions have the opcode of 0. So it'll be 6 zeros. So actually, we can actually decode this instruction. So because I say here we want to put it in machine code. So first thing we're going to do is we're going to have S1 plus S2 and store it into T0. So this is where we start using our MIP screen sheet. First, we go to our MIP screen sheet. And let's see if I can go back into Blackboard here for a second. And you go into Content. And you go into Reference Files. And when it decides it wants to download, there is the MIP screen sheet. So let's open MIP screen sheet. And everything we're doing is addition. So it's this instruction here, right? 0, and the function is 20 hex, which means 10, 20 hex. So hex, for those of you who don't know, means it's it's going to be 16 values. So you can go anywhere from 0 to 9, and then from A to F, right? So represent. So F is 9. So F is the 6th letter of the alphabet. 9 plus 6 is 15, which you represent as 1111 in hex. So this 1111 in binary is represented as F in hex. So in this case, let me see if I can find one with a letter. Yeah, perfect. F in hex. Load upper limit, upper immediate, which we won't really get into in this course. But the whole idea is set less than. You have an R-type instruction. You have 2A hex, so that's 10. And A is the first letter of the alphabet, so it's going to be 1 plus, and we can represent in digits from 0 to 9, right? So it's 9 plus 1 is 10, so that becomes 8, 10. So that's 2A hex there. So that's what that means. So going back to this first problem, we have to translate the MIP screen code. What this would actually be is 1, 2, 3, 4, 5, 6, since we know it's 6 zeros. And then RS is S1, so it's 16 plus 1. So if you look at your MIP screen sheet, the other thing it has down here on the second page, no, it's on the first page, it's my fault. register names, use and call convention. So we know S0 is here. Starts out at 16. So S1 is 16 plus 1. So it's all the way through S7. So S7 is 16 plus 7, which is 23. And we can see that it ends at 23. So since it's 17, it's 5 bits. And I'm just putting a space in there just so it looks clear. So it's 16 plus 1 is 17, is S1. We're adding S2, that's RT. So it's going to be 5 bits, 18 there. So it's 16 plus 2 is 18, right? Does that make sense? So this is S1, that's S2, that's the opcode. And then we have to do RD, right? RD is T0. So what's the initial number for T0? Since you have the green sheet open, it's on the bottom right. What's the initial temporary register for T0? Very good. That's exactly right. It's 8. So we want to do 8 here. 0, 1, 0, 0, 0. That's T0. How much are we shifting in this instruction? Y'all are overthinking it. It's simple. How much are we shifting in add instruction? None. Very good. See? We are not shifting at all. And then the function, for those whoever has the green sheet open, it's for add instruction is, I believe it's 20 hex, right? It's the very top instruction. 0 hex. So then we go 1 0 0 0 0 0. So now we have converted an add instruction in C, which is A and B, this first part. We converted it to register transfer language, and then we have now converted to the machine code. So remember the first day of lecture when I said you all the instruction memory? The thing that you spit out to the instruction decode is this. That's 32-bit value. And then this part goes up to our control unit. These go to the registers. This goes to the ALU for the shift. And this goes down to our ALU control. Remember that topic we got objective in section 2 where we had the ALU control and the function? That's this value here. So then, same thing. Most of these are going to be the same. So for the interest of time, I'm going to copy and paste there. Except the difference is for our RS, which should go here, T0. So we're going to make this 8, right? And this is S6, so that's 16 plus 6 is 24. And then we stored in S0 for our final solution, so that's going to become 16 here, right? So that's RT, I'm sorry, destination register RD is now this one. Shift amount's the same, function is the same. Opcode is the same. Does that make sense now? So now we have converted A equals B plus C plus D into 2 instructions of machine code. Yes, Heidi?
On that second set of bit code where it says 0, 0, 0, 1, 0. Mm-hmm.
Oh no, that should be 8. I was just running fast there. That's correct. Does everybody understand why I use the temporary registers here? Does that make sense? And so that is the solution. Go scrolling down here, I actually, in more detail, gave what we just did there, right? The question asks for the C code, MIPS assembly language, which is your register transfer language, and then the machine code, which is, that is sufficient.
So,
yes, Bridget. Yeah. As long as you write the right answer and everything asked for in the question. Yes, Alex.
Is there a reason why we ended with writing the S0 instead of the E0? Is there a reason why we ended with writing the S0?
Yes, because in the question we explicitly state where A is stored in S0 and is A equal, yeah. So the question is, why do we store the final solution in S0? It's because I explicitly stated in the problem. Any other questions about this before I move on? All right. This is another one, basically order of operations. So here, now we're all going back to middle school, right? Algebra, order of operations, no. Algebra again, boo. I don't want to do this anymore. The computer will do what you tell it to do, right? So before you have to add these together, you can't do this. You can't go. You have to do what the computer tells you. So first things first, we add. The problem explicitly states G is in S0, H is in S1, I is in S2, J is in S3, and F is in S4. So first thing we do is we take G plus H, which is S1 and S2, S0 and S1, and we add them and put them into a temporary register. So that's going to be add T0, S0, and S1, right? The next thing we have to do is we have to add I and J. And the reason why is because of order of operations. And we put S2 and S3, and we add them and put them into another temporary register. Now, a common question I get is, do we have to do T0, T1, T2, T3? No, on an exam, you are the compiler. You can pick whatever one you want, as long as these two that you choose end up being the two that you subtract. Right? And then you have to do it in that correct order. So a common mistake, someone goes T3 and then does T3 and T0. Why is that wrong? What the change that I made, why is it wrong? Yes, because I flipped them. Very good. It's no longer in the order of operations. So everybody is kind of going like that. Yeah. Let Teresa beat you so hot. That is the correct answer. So then what I've done in the next three steps are the same thing. If you look at the subtraction on your MIP screen sheet, the difference is that it's the same opcode. Subtract. Here, RS minus RT is RD, so it's in that same order. If you look at the MIP screen sheet, it's 2 hex. So then we go back down to our lecture notes, if it ever decides it wants to let me. And you see how here at the end, the function is 10. Let me scroll down a little bit here. 100010. If you separated that out into hexadecimal, these two represent the first number. So it's 2, and then 0010, so that it becomes 2 hex. So it indicates that it's subtraction. If you compare your topical guide objective, you'll see that your input for addition is 100000, and it's 100010 for subtraction, because that helps you differentiate between the R type for subtraction and addition. And if you see, there's only one bit of difference, right, between addition and subtraction for the. What can you do with that one bit of difference? Think back to your adder subtractor.
You can use that bit to toggle between addition and subtraction.
Right. And what does it specifically do? You're on the right path. You're very close. So what does that bit being 0 or 1? What does that change in the flow of the organization there? What it? Yeah. So you have the XOR gate, right? As well as the carry in bit. So you're carrying in 1 for subtraction, and then for 0, 1 when you flip B, you're using the exclusive OR gate. So you guys combined for the right answer. So I've put here a set of common mistakes. As you can see, I've put in this situation where people try to add or try to take I minus I minus J. The reason why that's wrong, even though it's logically correct, is because that is not what the compiler told you to do. Does that make sense? Let me scroll down a little more here. Okay, so up to this point, we have dealt with R-type instructions as addition. But now I've added a little thing in here. Translate the following C code to MIPS register transfer language and the MIPS assembly language and machine codes, right? Just like all the other ones. Assume G has already been loaded in S0, H into S1, and F is S4. Now I have this little thing here where it's F equals G plus parentheses H plus 5. So we've talked a little bit about immediate instructions. And the second instruction on your MIPS grid sheet is this add immediate value here. Okay? And the function is 8 hex. It's an I-type instruction, so it doesn't have, the opcode is 8 hex. It doesn't have a function value at the end. The last 16 bits in that I-type instruction are this sign immediate value. So that sign immediate value is going to be not the variable, but the value that you're adding to it. So we had H plus 5, right? H is going to be RS, and sign immediate is going to be 5. And then RT is where we're going to be storing our temporary value. So we go back to the lecture notes here. What we're doing here is we have add immediate. We have T0 for our destination, S1, and 5. So what we actually had is we had 8 hex as our opcode. So that'd be 001000 for add immediate. RS is S1, so it's 17. RT is T0. That's going to be our destination value, so that's going to be 01000. And the other 16 bits are going to be the value 5. So you have 9, 10, 11, 12, 13, 14, 15, 16. Right? Does that make sense? Because now this is the sign, that's sign immediate. So if we go back to the MIPS screen sheet, I bring this back up. Sign immediate here, sign extended immediate here. That's what that means. So we have 8 hex, which is what we put here. Then we have RS, so it's S1, T0, which is our temporary register, and that's how we get our sign immediate for addition. And then for the next part, we just add the temporary register, which contains H plus 5, and G. G is in S0. We now have T0, so we do it in that order. We add them together and put it into S4. Opcode is 0. S0 is RS. RT is T0, so it becomes 16. 8. RD is S4, so it becomes 20. 10100. Our shift amount is 0 because we're not shifting in this instruction. And then our opcode is 20 hex. And then as we scroll down here, we can see that that's exactly what we get. And on an exam, it's perfectly acceptable. You see this little, instead of writing out all 16, you see how I wrote There's a little ellipses right here. See that? I just went ... 101. It's a little bit of a waste of time on example. 0, 0, 0, 0, 0, 0, 0. That is there specifically to attempt to try to reduce your time on the exam. And so that's where that example ends there. So what ends up happening is we want to store this information either in the registers or in data memory, right? So if we recall the load store purpose of MIPS and the benefits of that, one of the benefits is we want to improve the high performance execution of compiled code. One of the issues here is that we want to pass what are known as pointers to the function. And one of the challenges is pointers are, and we'll define them here in a moment, our pointers are a location, is an actual numerical representation of a location in memory, not the value itself, right? And so the difference is, if you're looking for an address to somebody's house, the numerical or the value is, Greg, and the house number is 8120 Murphy Road or whatever. So that's a pointer telling me where Greg lives, but it's not Greg, right? So if I say, where does Greg live, and you say Greg, that's why if those of you who have ever done C++ and you get a segmentation fault, it's like, where does he live? Phil. And computer goes, that's stupid, I'm going to shut down. And that's what's known as a segmentation fault. Because what ends up happening is, when you say, it's all represented in 32-bit numbers, right? So you're saying, give me a location, and you're using a name representation, and you're actually doing the numerical value, but it's outside of what's represented in that memory, right? For that function or program. So when you go outside, it's like, hey, you're outside of the segment that we've allocated for this program. Therefore, you have a segmentation fault. So if you recall base addressing, what's happening is we're doing a load word. In load word instructions, we say S0, and it's going to be a 0 and S1. Here is what that means. S1 is RS. That is the base pointer to where I'm going to. The analogy I had, was the house address. The house address is the road, that's RS. So if I'm going to say, if I'm trying to get to Milwaukee, right? And I come in here, and we're saying, and this, this is the aisle. So RS is pointing to the aisle, and the offset is the third desk, right? So I get down there, find the third desk, 1, 2, 3, and then I have to find first chair, right? So pointers are telling me specifically how far I need to go down the road to find it. So what ends up happening is I get the actual value, which tells me precisely where the aisle is. So this base addressing is saying, all right, I have some sort of binary representation of each number of desks, right? And then it gives me the third desk, so it would be 00011, right? That would be the value in RS. Gives me the actual value of the register. And then I need to know the offset. The offset in this case is 1 because 1 is the first chair. That is the value that's in the immediate. So since we use byte addressing, everything's going to be multiples of 4, right? So if I want to do that, I have load word S0 4 S1. That tells me here that I need to go down. Here's the base of the array. It's here. This is the first block. That's block 0. And then the next block is block 1. I go down there. I find my information. That's what a pointer is. So what can happen is, if I want to get this piece of information, I do a load word, I grab it, and then I put it back into the registers in register S0. So this means this is where it's going to end up, and this is this is the pointer, and this is the offset. So If I recall how to do this, first thing I want to do is formally define pointer. A pointer is a variable whose value is the address of another variable. So int star sum is the value of the address of sum. Does that make sense? Star sum is not sum. Where does he live is not Greg. In base addressing, the pointer is the numeric value stored in RS. And the offset is the sign extended immediate value. And I'll give you guys a minute here to write that down, and I'll show you on the MIP screen sheet how that corresponds to the register transfer language. Actually, I don't need to go to the MIP screen sheet. I can scroll up just a little bit, and it's written right here. So if you look at load word, the register value of RT is going to be equal to the memory address of the value of RS. So you have the register RS, right? You do 5 to 32 decoder. You get that value out of the register. You add the sign immediate. All of this right here is just that base addressing drawing. You get the value from the register. You add the sign immediate value that's in the instruction. You go to data memory. You physically get that value that's at that location, right? That is represented in RTL as M of block. Remember when we were doing direct and set associativity, and I said M of, sorry, that I was going DJ there for a second. Slim. So remember I did this, and I kind of for notation said M of 23, right? What that means is I want the value at 23, not 23 itself. Does that make sense? That'll help you as you kind of review for the exam on Thursday. And then we get that value, and then we put the value at where the location of register RT. So that's your register addressing. And then the opcode is 23 hex, so it's 100011. And then this assembly, which is what I've referred to here, the notation you'll typically see in code, the value that's in the sign immediate is put before a pair of brackets with the RS there indicating which register. And then RT, where you're going to store it, is on the outside. So if I'm going to get, if the pointer to the array is stored in S0, and let's say the array is A of 3, right? And the base pointer is in S0, and I want to get this value and put it into a temporary register T0. What this means is I want to do a load word. I want to store it in T0 eventually, right? And since we're doing base addressing, we have to multiply by 4. So it's 3 times 4, so that becomes 12, and that's what the compiler does. Compiler-driven coding of the micro engine. And S0 is here. That's what this means. So for 4.2, load word instructions are instructions that take an address calculated by the ALU and loads the value from that address into a register specified by the instruction. So load word is an I-type instruction. Its register value of RT is equal to the memory value that you can find at the pointer of RS plus the sign extended immediate. And the opcode is 23 hex. And 23 hex, RS, RT, sign immediate. So it is an I-type instruction. And so the next thing we're going to do is backwards. So load word gets something from memory and puts it into a register, right? The other thing I need to do is I need to be able to take things from the registers and put them into the data memory for storage later. So load, get it from data memory, load it into the registers, store, take it from the registers, store it into data memory. So store word is backwards, right? So store word is going to look like this. Store word T0, and we'll just say 8 of S0, right? So what this means is I want the value that's in that temporary register. I want to go to the array, so let's say it's A, and the value of the sign immediate is 8. So what element of the array do I want to put it in? What's that? Correct, second one, because it's 8 divided by 4, because we're doing byte addressing. So it's 2, A of 2. Very good. So we formally define store word instructions are instructions that take an address calculated by the ALU and stores the value from a register specified by the instruction to that address in memory. So what this means here is we're taking a value from the register and we're storing it. We're using the ALU to calculate the address in data memory and putting it in that location. So here we're actually taking Greg and dropping him off at his house. And it's 2B hex is the opcode. So you have 101011 is your opcode. You have RS, RT, and sign immediate. And in your assembly, as I've written up, the assembly is equal to store word RT, sign immediate RS. So it's just like the same thing. So basically RT in the case of load word and store word represents the location in the registers. RS is the base pointer in memory. No. What's wrong? Nothing? Okay. It's pretty rare just to have a student just look at it and go. Well, example 4.4 is a really good way of clarifying what I mean by all of this. Because what we're doing is we're going to take some C code. It's this is actually AF7. I can zoom in a little more. There we go. A little more. And so we're going to translate this following C code from MIPS assembly, register, transfer, machine language. So I have A of 8 equals A of 7 plus C, where I have C stored in S of 3. The base pointer of the array is in S5. So this is how load and store word works. I have to get the value from data memory. If we recall from the topical glad objective, we perform all of the operations in registers, right? So I have to get the value from data memory, perform it in the registers, and then store it to data memory again. So the first thing I need to do is I need to get this value of 7 and know which element of the array that I need. So how do I take 7 and what's the value going to be of my sign immediate? What type of addressing do we use in MIPS? Well, that's base addressing is for byte addressing. So byte addressing is specific. Whenever I ask what type of addressing do we use in MIPS, I'm referring to byte addressing. So byte addressing means we have to do what? What's the fixed size of buses in MIPS? Buses, instructions, everything is how long? 32, right? And what type of addressing do we use in MIPS? And how many bits are in a byte? So if we have 32 bits and I have 8 bytes in a memory element, how many elements do I need to represent the 32 bits? 4. So if I'm A of 7, which element I'm actually going to start at. No. I thought you guys would jump all over this once I got you to 4. Yes, there's what I've been wanting to hear. 28, right? So here's the way this byte addressing works. So S of 5 in the register, I get the value, so I get R of S of 5, right? So that's what it looks like. That value goes to data memory, and A of 0 starts here, right? I need the next 4 blocks to represent A of 0, correct? A of 0, A1, 2, 3. So then A of 4, so the 4th block, 0, 1, 2, 3, the 4th block represents A of 1, right? So in order to get this value, you just multiply by 4. So which value am I starting out there? 32. So what I mean here, when I say 28, I want 28, 29, 30, and 31, because 28 represents 8 bits, 29 represents 8 bits, 30 represents 8 bits, 31 represents 8 bits. You combine them together, and that gives you a 32-bit value, which is then what you take and store back into the register. Does that make sense? So what I'm going to do, I'm going to do a load word instruction. So it's going to be load word. I'm going to store in a temporary value, T of 0. And then the sign immediate is 28, S of 5. Because we explicitly state in the problem that S of 5 is where the base pointer of the array is. So S of 5 tells me to go to row 3. 28 tells me to go to 7. No one's sitting in 7, so the value would be 0, right? Then I get that value, then I bring it back to the local registers. So the next thing I need to do is perform some sort of calculation. So I do add, right, because I'm adding T0 and C, right? Now what you'll notice is that you don't, for the rest of the problem, you're not going to need that temporary value after you add, right? Not going to need it. So some people will do this. They'll store it back in T0 and S3. This is also correct as long as whatever you put here matches the store word instruction. So the store word, so let's just say for clarity, we'll put T1 here, right? So the store word instruction is going to be T1 of 32 S of 5. Who here is confused by that? Everyone's got it, even though I don't see a lot of smiles.
Let's take what's in T1 and storing it in S5.
Correct. So this is data memory. Oh, green. Data memory, register, registers. Does that make sense? These, and if you recall from the performance question, remember I said that load stores, if you don't properly design your cache, can take up to 100 times longer. So you typically want to avoid these as much as possible, which is why I said that you want to be able to do these local registers adding very quickly. Here is unavoidable because our coder has asked for arrays. And so I wrote a lot more than you would need to explain it, but here, as you can see, that is what we came up with for our solution right there. Load word, T0. You can do T0, you can do T1 for that, and it works out fine. So what happens when the element in the array is a variable and not an integer? So so instead of saying, let's say I did a of 8 equals a of b plus 7. I keep throwing nastier and nastier little pieces of code at you, right? So there's some value in a register, b. Let's say b is equal to 5. What's the value that I need to get to the array? 20, right? But b is in a register, and the instruction has a sign immediate, right? So that's where things start getting a little nasty. Plus, I need to somehow convert 5 to 20. Does anybody have any ideas? I've told you everything you need to do to solve this problem, other than okay, there you go. Now he's looking at me. All right, good. So, what do you guys suggest I do here? So here I have a of b is 7, right? So as an example, I said b could be 5, but it's a variable, not an integer. So in the previous problem, we were able to just put in the integer since it's a compiler. But we don't know what b will be until we actually get to that point. So we have to do something else. Any theories? You guys seem exhausted today. What did they do to you? Well, first thing, let's start here. If I wanted to get the value of b times 4, what instruction could I use? Okay, bit shift by 2. What is that instruction called in MIPS? Look familiar? SLL? What is it, Travis? You recognized it. Shift, left, Spock. Hint, that's what does Spock say to Kirk all the time? None of you are Star Trek fans? Come on. That's highly illogical, Jim, right? Shift left logical. My goodness, you all are dead. Okay, so I have a equals b plus c. So let me tell you how to do this. So 4.5 is a plus b plus c. First thing you want to need to do is you need to calculate b times 4 and store it in a temporary register, because we don't know what it will be until we actually get there. So we do shift left logical, and we do temporary register T0. B is stored, part of the problem is stored in S1, and we put it in 2. So what we're doing is we're taking the value of B, we're shifting left by 2, which multiplies it by 4, and then we're storing that value in the temporary register. So next we have our base address in A. In fact, I might be able to just here we go. Let's get rid of all that. That might be just more causing more problems than solution. Step 1, shift left logical. So we've stored the temporary register. We have S1 is B and 2. So that we can put in our comments is B times 4, right? So far everybody agrees? Good. So now we know that the base of the array A, we now know our offset, which is in T0. So what we can do is we're going to create a second pointer that's going to point directly to the element in the array that we want. So we're just going to add them. And we'll say, to make it simple, we'll say T1, and we add the base of the array, S5, and our calculated offset, T0. So now T1 is a pointer to A of B. Does that make sense? So we've created a second pointer. And now I'm pointing exactly there. So it's like in this case, if I'm trying to get to the WAF, like it was earlier, first I had to take my sign element and do my offset. Now I have something that's pointing, that's Nawaf's house right there, right? So now I can just do a load word. We'll do T2 here. And since it's pointing directly at it, it's just T0 of T1. Does that make sense? So now I have the base pointer, instead of pointing at the array, T1 is pointing at A of B. It is pointing here, right? It's pointing there in memory. So if this is our memory, S5 is pointing here. We calculated the offset, and now T1 is pointing at A of B. So I don't need any more offset, right? If I know where I'm at, I don't need to screw it up. So 0 is going to be our sign extended immediate value. And that we're going to put that and load it into T2. Then the next step is to do, this should be the easiest one. So now I have A of B loaded into T2. What do I need to do next? Yeah. Add S3, T2 and S3. And we're going to do T3, where we have T2 is going to be A of B, and S3 here is going to be C. Right? So the next step is, oh man, now we're back to our variable again. So what we have to do is we do the same 3 steps. So the steps are, so now that you know, what do I need to do to D? Shift left, store it in where? Temporary register. So see if I can do this in smaller. So shift left logical, we'll just call it T4. And then we got D, which is S4 here, right? And then 2. Right? So now S4 is our offset, right? We know how far it away is from the beginning of A. So what do we need to do next? Add, because we're creating a pointer directly to A of D. So we're adding to our offset now. So we're going to add, we'll just call it T5, and then S5, which is our base of A, correct? And then T of 4. And then we're going to store a word, just like here. We're going to take our value that we added together, T of 3, and we're stored in 0, T of 5. So we created 2 pointers, one to get A of B and one to store A of D. And in order to do that, we had, since we don't know what B and D are going to be at the beginning of our function until runtime, we have to calculate the value of B that's multiplied by 4. We have to calculate the value of D that's multiplied by 4. And the reason we wait until the end here is I won't get into that until multi-threading. But we calculate D times 4, which is shift left logical 2. Add it to the base pointer of the array, and then we store it. So let me get the cleaner version up here in black so everybody can see it. So here I explain everything in detail, and I separated it out. Let me get rid of the little comments here so you can see them all together. And you can see, just like we came up with, that the optimal amount of code, for those of you going over the video, this is a deal correct answer. And then the assembly language, again, is to get you to go back and look through the R-type instructions. Shift left logical is an R-type instruction with 0, except with shifting, it has a shift of 2, right? So we know our 2 shift functions are here and here. Right? Okay. So what we're going to do, we're going to stop this lecture here because that's getting into branch, and that's a good way to start out next Tuesday. Before I dismiss you, you have me for 8 minutes. Opportunity to ask me any other questions about the exam. Yes.
Is this section 4 that we're going over now?
No. Today's lecture is not going to be on the exam.
So, like, what chapters and TGOs?
Everything through sections 1 through 3. Everything up through Thursday's lecture will be covered. Yes?
This is more about the TGOs for this.
Okay, yeah. Okay. I already know the question you're going to ask. The TGOs that for today's lecture are due next Tuesday. Yes?
What's the format of the test?
The format of the test is there's the take-home portion, which will be available at 11 o'clock. Follow the directions on those. Turn that in at 9:30, as I've indicated on the cover sheet. Then the in-class portion will be basically, if you recall from last lecture, remember this, exam 1 review. It'll be the exam, if you look through the TGOs that correspond to these questions, and TGOs and example questions that correspond to these portions, and you write that out, your exam will be some subset of that. Yes?
So when we're doing our resume, are we going to try and act as if we do know how to do some of the stuff that it's asking for if we don't specifically know?
You don't include it yet. You will be building your skills. I should not be encouraging you to lie on your resume. Well, that got your attention on the load board. It was like I was stabbing you all in your heart. All right, so now we have a pointer. Oh, just make it stop, Dr. Munson, make it stop. Yeah. So as you build on, you're going to be more and more qualified. You know, for example, on there they're asking for registered transfer language. By the end of the semester, as you're starting to see, it's pretty complicated, but you'll have plenty of practice and opportunity to build up on it. You'll know C, you'll know RTL, you'll know Verilog and VHDL, especially by the end of 386. Once you go through all the cadence stuff, you'll have a lot more opportunities to build on your skill set. But I do go into the video in a lot of detail about some of the things I expect and don't expect. So the TLDR version is put what you can in. Something I mentioned in the video is even if you have something like you babysat dogs, or you had some sort of what would be considered a remedial job, there are ways to intelligently convey some skill that you had to use in that job. For example, let's say you were like me, and you had to work at this place called Preston's Country Club for Pets, where basically my job was clean up dog food, right? I worked landscaping, and we got a drought, and I got laid off, and now I'm cleaning up dog food for the rest of the summer. What were some of the things that I had to do to demonstrate that I was responsible enough to do another job? Well, I had to make sure the place was clean. I had to be responsible, because you can't have somebody come back and there's just dog poop everywhere, right? So I can complete tasks. Also, I had to coordinate other people to make sure they were doing it, right? That shows responsibility, teamwork, because you can't just go like, Teresa, how many times have I told you to clean up the dog poop, right? Eventually she's going to, you know what, screw him, and leave, right? But you have to use some sort of leadership and teamwork ability to say, hey, if we get this done faster, then we can do other things that don't involve having to clean up dog poop, right? There's positive ways to convey even what seems to be a remedial job on the resume. And like I said, you get 3 cracks at it. Just make an attempt. if I see a conceptual error as how you're building it, you'll notice it on my remarks, and then you go, oh, hey, I won't do that. So the second time it gets better, and by the third time you do it, it's easy, right? You got me for 3 more minutes. Any other questions? Okay, I have to run an errand today, so I'm going to miss the first hour of my office hours, but I'll make it up because I have 12 to 2, so instead I'll be 1 to 3.